Uh, the talk is given in its title, basically. It asks the question, was impact sedimentation common enough? Something had to happen, all that stuff that was knocked out, and it didn't all turn into spherical layers, uh, to uh, make it so you don't need a warm and wet Mars climate until very recently. First, the spherules are not concretions. Uh, I got into this in 2004 when the first images came back from Opportunity of the blueberries or hematite hailstones at the Opportunity site. And they were called concretions. And they didn't look like any concretions I'd ever seen. And my co-author and co-worker at the time, Paul Knauth, who'd worked on a lot of Archean and Proterozoic spherical beds, didn't think so either. So that got us into that. And over the last 15 years, three rovers have imaged lots of layered rocks, and none of them really look like they're water laid. They all look like they could have been laid down by turbulent clouds with lots of shear. If Mars was warm and wet, to lay down all these rocks, the ones in Gale Crater particularly, imply warm and wet until about 1.4 billion years ago, according to crater counts. And that, of course, is long, long after the events we just heard about, 2 billion years or so afterwards. It's always been very hard to make Mars warm and wet for longer than maybe a few hundred years due to large impacts. And the rocks we're talking about in late Noachian to early Hesperian are much younger than that. Confusing matters, possibly volcanism, possibly late impacts, caused a lot of acid vapor alteration to the entire Martian surface, including the surfaces where the three rovers landed. And inside Gale Crater, at the bottom at least, neutral groundwater extensively altered earlier deposits. These are not shales, they're just hydrated dust, basically. What could have done all this? Basically, turbulent density currents. On Earth, they're commonly called pyroclastic density currents, or PDCs. People on Earth have recently started calling impact-generated ones IDCs, or impactoclastic density currents. You also find them for nuclear blasts, which is where they were first described. This is at a little one at the Nevada test site. I grew up watching these on television. That's how old I am. They're also very well described in Hollywood movies, although this is an actual one without dinosaurs running in the foreground, as due to volcanic eruptions. The volcanic ones, the ones on nuclear ones are not due to water in the substrate. They're due to the presence of an atmosphere. The ones for volcanics could be partly due to the atmosphere and partly due to water in the magma, depending on how silicic they are. In any case, they are potentially huge. Pinatubo certainly was and affected Earth's climate, but they're just giant steam explosions. They don't have nearly the energy release per unit volume that nuclear or impact ones do. And close to home for me, here in Arizona, there's dust storms that form purely from cold air. That's a downburst, explosive downburst from some thunderstorms that can down airplanes, so they close airports during these thunderstorms. The cold air picks up all its dust by scouring. These are infamous for going 100 miles or more. This one started down in Tucson about 90 miles away, and kept going until it ran out of steam or whatever it was up near the Mogollon Rim, and then sort of turned west to California. Notice that because of climate restraints on the electronics, the 3 rovers are all near the Martian equator, and the 4th one won't be too far either. And they also just happen to be right at the edge of the topographic contrast between the lowlands and the heavily cratered highlands. Any density current that's heading downhill, and they all do, just like water and steam, just like water and lava. They head downhill. It has to pass by Meridiani or Gale or Gusev. Where the rovers landed was flat ground at the bottom of the crater in these 2 cases, and just plain flat ground here. They're not areas that are going to be heavily eroded except by the wind. Since this meeting was supposed to take place in Hawaii, here's a small field trip. The beautiful crater in downtown Honolulu. It's not a raised rim, it's just pyroclastic deposits, crudely layered. And if you look at them in detail, they are just gravelly and poorly bedded, and they probably look somewhat like the layered deposits of a rampart crater would look like. If you look between layers where there's high shear, you can find small zones of low angle crossbeds. A more interesting one from a Hawaii field trip is Coco Crater, which is a few miles down the coast and is identical from the air. But if you go down to ground level, because it's a kilometer or more displaced from the ocean, most of the deposits are finely layered. They look just like Mars, and you can, if you look through tourist photographs with tourists in the foreground, you'll see lots of rocks like this in the background. They have low angle cross bedding throughout. Where they've cooled off, you find polygonal jointing. This polygonal jointing in Gale Crater was mislabeled as mud cracks, even though it has none of the characteristics of sedimentary mud cracks. That is, it's just joints filled with calcium sulfate like every other joint that's been found on the surface of Mars, every other fracture. You also find festoon-like cross-bedding, this was called at Meridiani, as evidence for water flowing across the surface of the alleged sand dunes, which kind of is bizarre, particularly since the water didn't alter them particularly or erode them. These, of course, are topographic. Wherever you find a little gully, you see a promontory that's sticking out, and if you're 6 feet up like the mass cam is, then you're looking down and you're going to see just like looking at a topographic map. One of these, Gusev, had a little bit of basalt sitting out at the end, and they called that a bomb sag and used it as an indicator of volcanism, even though there was no volcano anywhere near and plenty of young craters nearby. Here's a real bomb sag. It really destroys the bedding. There's lots of them around. They're typical of Mars. Mars, a steam explosion volcano. These Diamond Head and Coco Crater were because basaltic magma coming up the dike intersected seawater and blew it up. Big steam explosion. You also see accretionary lapilli, which are typical for pyroclastic deposits and also for impact deposits. They're spherules, they're concentrically banded, and they are not concretions. Some more comparisons. The rocks at Meridiani were called dune sands. These are actual dune sands. As you study in freshman geology, the dune comes down this face as at the angle of repose, at a steep angle. In contrast, the dunes that you see this is another mar in New Mexico with better exposures. The dunes that you see there are dunes that you might form in a Category 5 hurricane. Really high speed whoosh going by. The rocks that have been called dune sands in Meridiani are identical. Everything is eroded off, very high shear environment, very high speed. Density currents flowing by, pyroclastic density currents can go much faster than a car can drive. Again, this very low angle cross bedding is typical, and planar erosion surfaces by scour are typical. These are the alleged dunes at Meridiani. These are identical appearing pyroclastic deposits allegedly at Gusev. There's no volcano. They are slightly coarser at the bottom, and there was the putative bomb sag. Of course, ejecta have been known to come out of impact craters also. A unique feature of high shear environments is planar erosion surfaces. The one at this has appeared in all the textbooks, and they show this little trough here, but there's no discussion and no explanation. It's very hard to explain if this is the water table, which has been claimed, and the spherules, which allegedly form by groundwater, are just as common above the alleged water table as below, so you need some kind of a yo-yo water table. And you find identical planar bed forms at the bottom of what is claimed to be a lake and Gale Crater. The only difference between these sediments and these sediments, these are a little finer grained, and they're hydrated by groundwater, somewhat variably. This is alleged lake beds with low angle cross beds. This is higher up. A year later, low angle cross beds and clay rich layers. These are not wind, and these are not water. If you look at Gale Crater, the rovers are down here, or the rover is down here. This is the Peace Vias alluvial fan. If you look at it in detail, or an image of the day from Themis, it sort of disperses without any distributary craters. It has a very low crater density. It doesn't have much feeding it. But if you look a little further uphill, which the photos never do, you'll see a very young layered ejector rampart crater, which could have provided plenty of sediment for this stuff. We saw some rounded pebbles this morning that no one called water laid. These are similar pebbles from Germany. Rounding simply indicates abrasion. It doesn't indicate water. It would help if there was a channel, a river with rounded pebbles in it, but there isn't. These are the mud cracks, real ones filled with sediment from the next layer up. Polygonal cracks filled with calcium sulfate are normal joints on Mars and indicate nothing. This is concretions, real ones. Some are round, some are not, all different sizes, whereas the ones on Mars are limited to 5 millimeters. They consist mostly of sand, even the round ones. This is a textbook illustration of concretions. They clump together. Bedding passes through that are more likely to look like flying saucers than uh, than spheres, although they can be spheres. And again, clumping is very typical. These are actual concretions, and huge varieties have been described from Gale Crater, whereas this is a blueberry that appeared in Gale Crater. These are accretionary lapilli. This is from Kilburn Hole, concentrically banded. They look like the ones we saw from Hawaii. This is from the Sudbury Impact Crater, concentrically banded. These are the blueberries at Meridiani. There are some doublets and triplets, but they're much smaller because they had to be suspended in air. So where you find ones stuck together, they're only tiny ones stuck together. The big ones are singlets. You find identical ones at Gusev, which have been passed over. So that's my summary. If layered rocks on Mars are from density currents, or at least the ones you see at the surface and from orbit, then you can make a Mars have any climate you want, including hot. They are not preserved very well on Earth. Earth analogs are terrible, only volcanic. Whereas on Mars, because it lost most of its atmosphere, when they were being deposited, they should have been depositing in quick succession and left. The very primitive basaltic composition, the lack of any shale, the spherules, all the other characteristics I just went through argue against liquid water. And there are no features like channels, other than giant one streams from orbit, that would be characteristic of liquid water. As Jim just discussed, you might find older water deposits anywhere on Mars. The problem is superposition. Rovers can't dig, they can't drill, and what you see from orbit and what you see spectrally is only the youngest stuff on the surface. So there might well be water-laid deposits deeper in Gale and Gusev and underneath the lavas. Gale and at Meridiani and underneath the lavas and Gusev. But what the rovers are imaging and what has been described as water-laid is not. And I'm done.
Thank you so much, Don. That was wonderful. Does anyone have any questions? We have a few minutes for questions, if there are any.
At the moment, there are none in the chat.
This table shows some of what you might expect to see in liquid water deposits that you don't on Mars. The other table shows everything that you see on Mars that is not consistent with liquid water, but is consistent with impactoclastics, at least on the surface. And this is just spherules, accretionary lapilli versus concretions. They're very hard to confuse them, but if you're looking, people see what they're looking for, people see what they expect to see. People, particularly in the case of NASA, people see what they proposed to see. So it's easy to make mistakes.
I'll ask a question. I'm not fully up on a lot of this stuff, but what is the counter evidence for them being the concretions? So what is it about them that's making people say they are concretions?
They are clumped. What's been passed over is that where you find two of them together, both are half size. Where you find there's another doublet, and some of them are have deposits on top. These form in sticky condensates by condensation of acid metal-rich steam, fumarolically, if you will, as I displayed here, and they're sticky. So they stick to each other. And if they continue to build up deposits on the outside of dust and the other stuff that sticks to them, then they come down as doublets or triplets. The doublets and triplets are very rare. This particular picture I included because it included a lot of them. I never saw any pictures with as many as this picture has. But they were used initially to say these have to be concretions because they can occur in doublets. What they ignored is that there are the big ones that are very size and shape sorted, very peculiar. And the paper on the real concretions in Gale Crater, which described 9 varieties, did not compare them at all to the blueberries.
Thank you.
I think there is one question in the chat. Stuart, do you mind to take
Yep, it must have just popped up when I blinked. Earlier papers have referenced melt flows extending out many crater radii. Would the concept of impactoclastic density flows fit better?
These are distal. Melt flows would be proximal.
Okay, Clark.
These are very fine grained, except for one bottom layer at Gale, but the rest of them are very fine grained, and they are much more distal than you would. The ones in Hawaii are not very good examples because you're only a kilometer away from the crater. But the problem with pyroclastic deposits is they literally run out of steam a lot sooner than impactoclastics because they're just steam explosions that aren't releasing nearly the energy of a decent sized impact.
So Clark Chapman has just a comment, I think. He says that you've made these arguments for many years. For some reason, I gather they aren't widely accepted. There must be people attending the meeting who could say why they think these can't be impactoclastic in origin. In the interest of time, if you have a very quick response to that comment, otherwise we can save it for the discussion.
People see what they expect to see, and that's the kindest way to put it.
Fair enough. All right. Then, Clark, if you want to discuss that more during the discussion, we will have time later.
Excellent, thank you.